Just wanted to say again, well, quiz 1 is come and gone. From what I see, what do you think? Too easy, right? Yeah? I don't know. I haven't got the grades yet. One TA said sections did pretty well. I don't know. I haven't seen the grades yet. But we'll have those up for you. You'll have them back next Tuesday. But we should have the scores up before then. I'll remind you again that we are recording these lectures and we put them up at a YouTube channel. You can find that YouTube channel just by going to YouTube and Google the Kernel Chem 2046. And you will find a YouTube channel where all these videos are placed. Just in case you wanted to, I know what it is. It's like, hey, the Colonel told that really funny joke during class. I want to go back and hear that again. No. All right, now, we have to switch gears. We're done with chapter 17. And we're moving to chapter 18. Quiet. Shh. Yes?
So we're obviously not going to finish chapter 18, so how far into the chapter 18 homework did you go?
So the question was, we're obviously not going to finish chapter 18 before exam 1, right? Yes, that is correct. We're not going to finish. Exam 1 is next Thursday. So it's going to cover all of 17, and we will make a denotation. It'll probably cover up through the section on strong acids and strong bases. But I'll refine that on Friday, yes.
Do you give out any practice exams?
I do not give out practice exams. I do not. However, I would add that I'm sure you can find them online. 100% sure of that. Yes?
Does Broward Tutoring have anything that they can help us with?
Broward Tutoring, I don't know what Broward Tutoring is.
Okay.
What is it?
It's tutoring for classes.
Tutoring center.
They specify
But-
in each section.
But is it associated with, quiet please, it's associated with the university.
Yeah, Broward's right over there.
Oh yeah, I know Broward, okay.
Yeah.
Look, okay. I'm not exactly the most tech savvy guy in the world. Guilty as charged. Okay? Yes.
Are you going to post a breakdown of the exam?
Breakdown of the exam.
How many questions from each chapter? Like what type of questions?
No, not going to do any of that. No. Look, let me give you the bottom line with regard for me on all of this. Do I give you exams? Do I break things down? This, that, the other. Can I give you more in some way? Well, every semester I give out too many A's and B's. The percentage of A's and B's that I give out is a little bit higher than most people. And so if you tell me, no, Colonel, you need to make more opportunities to make it easier for the students to do better, I fall back on, well, I'm giving too many A's and B's already. Why would I want to make it easier? So that's the answer to all that question. Now, and it's a very good point. We will not be able to get through, obviously, all of the acid-base chapter 18, before next Thursday. And so we'll cover up through probably the section on strong acids, but let me see how far I get so we can refine that. All righty, acid-base chemistry. I've already given my sales pitch about why acid-base chemistry is important. I don't need to give you that sales pitch again. It's the essence of life's science. That's the bottom line. It's the way energy is stored in living systems by acid-base chemistry. So let's delve into a little bit of the history and definitions of this acid-base chemistry. You can go back through antiquity and people. What really helps us with acid-base chemistry is the sense of taste. Because things that are acidic taste sour. So things like fruit juices and vinegar, acidic taste sour. And so even in antiquity, people grouped substances together in terms of that acidic taste and knew that they had a common origin of some kind in antiquity. And then, I think I mentioned this earlier, bases have this characteristic slippery feel, and also they taste bitter. And I think I mentioned to you, when I was a kid, at least once or twice, my mom washed my mouth out with soap. The last time was actually 2 years ago. Anyway, see, that's one you're going to want to go visit on the webpage. You can get another chuckle out of that, just like you did here. All right. Anyway, so this characteristic bitter taste and slippery feel, and the quintessential thing would be soap, has that. So these things have been known since antiquity. And then this guy who I very much admire, Svante Arrhenius. You've already encountered the good Professor Arrhenius. He was a Swedish chemist, physicist in the late 19th, earliest 20th century. I believe he may have won the first Nobel Prize in chemistry, first or second Nobel Prize in chemistry. Might have been the first, right at the turn of the 20th century. You encountered him already when you studied chapter 17 of the textbook, which is kinetics. Famous kinetic equation, the Arrhenius equation. But Arrhenius did more than that. He was the first to, or at least given credit to be the first to identify what it is about a substance that makes it acidic and what it is about a substance that makes it basic, or at least for solutions. And Arrhenius said, so this is Arrhenius definitions, you might call them. Arrhenius said, a solution is acidic due to presence, here, ESENCE, of H plus in the solution, where of course H plus is our friend, the hydronium ion. And we've already established that H plus is a proton. H plus is a proton. It's a subatomic particle. Kind of weird, isn't it? Nevertheless, you can take that subatomic particle and throw it into water. It's very happy in water. But what happens, of course, is you can take this to the bank and say, one of the things Colonel said was, ions in water are never naked. Ions in water are never naked. So that H plus, we know the water molecule is shaped like that. And there are two great big lone pairs here. And listen, I'd like to teach you things beyond freshman chemistry. I'm going to give you one right now, help you understand science, help you understand engineering, help you understand the world around you. One of the most powerful concepts in all of science is the concept that opposite charges repel and unlike charges attract, right? So that's basic electrostatics. Two positively charged species will repel each other. A positively and a negatively charged thing will attract each other. This is called electrostatics. You can explain huge swaths of chemistry and physics just from electrostatics, just from the notion that opposite charges attract, like charges repel. So here's this water molecule. We say because of all these electron lone pairs, that this side of the molecule we say has a partial, that's a small delta, a partial negative charge on that side of the molecule. and we say this side of the molecule has a partial positive charge on that side of the molecule. We say that this molecule is polar because it has poles. It has a partial positive pole. Right. Okay, so the water molecule has a negative pole and a positive pole. And so what's that negative pole going to do? It's going to love that hydronium ion. It's going to love that particle, that positively charged proton. So there's that positively charged proton. A randomly walking water molecule slams into it and says, wow, my negative side really likes your positive side. Let's get together. That's called hydration. So this is why I say ions in solution are never naked. They are hydrated due to the simple idea of electrostatics. Opposite charges attract. So we've got this polar molecule, and so we might say that in reality there's that subatomic particle, the proton, and what it's got, I'm going to leave out the lone pairs now and just draw, we often call that a dipole moment. We give it a little arrow like that. And we put the side with partial negative charge there and the side with partial positive charge there. So it's an arrow. The electrons are like the point of the arrow. And so we know in solution that in fact the proton is not naked. It has, depending on temperature, etc., a number, as many as 6 of these things stuck onto it. Now, they exchange with the bulk water out in the solution. It's not like they're permanently glued to it. But at any given time, there's 4, 5, 6 water molecules with their negative heads butted into the proton. That's called hydration. Every ion in water does that. Chloride, sodium, potassium, calcium, magnesium, iron 3+, cobalt 2+. All ions are hydrated in this way. No ions are naked. And so that's why we go way up here, what I was talking about. We get lazy. We don't want to draw all those hydration waters. So we just call it H+. But we know that that's not physically right. And the other way, which is convenient for us to depict it, is H3O+. Now that's getting closer to the truth, because that means you're assuming you got a water molecule that is very strongly attracted to that positively charged proton. But both of those things are simply approximations of what the hydronium ion looks like. But you can take it to the bank that hydronium ion has water molecules butted up against it with this negative dipole pointing into the thing. So Svante Arrhenius said acidity is due to the presence of hydronium ion in the solution. Here are 2 ways that we can depict hydronium ion, both of them approximations. And Svante Arrhenius also said a solution is basic due to presence of hydroxide anion. Now again, all of what I said about proton is also true about the hydroxide anion. It is not naked in solution. And so you can say here's a hydroxide anion. We can think of it being the opposite case, that the water molecule is now oriented in the opposite way, with the positive end of the dipole pointing in and the negative end of the dipole pointing out. But again, the notion that this thing is not naked, it has 1, 2, 3, 4, 5, 6, depending on the temperature, depending on the ion. It has water molecules associated with it, and we call that concept hydration. All right, so Svante Arrhenius helped us out a lot. He said acidic substances are due to hydronium ion, and basic substances are due to hydroxide. So now, the question then becomes, how does a solution get hydronium ion in it? And how does a solution get hydroxide in it? And one obvious answer is, well, you take pure water, it's neither acidic nor basic, we'll get to that in a second, and you squeeze a little lemon juice in it. I drink tap water. You guys drink tap water? Who drinks tap water? Who drinks bottled water? Only bottled water. Yeah, I like to drink bottled water, but that's expensive, So I drink tap water. But I always have fresh lemon, and I squeeze fresh lemon in it. That way it doesn't taste terrible like tap water. So there, a great example of how to get hydronium ion into a solution. The citric acid in that lemon has a significant concentration of hydronium ion. All I got to do is squeeze it in there. Now my water is acidic. Okay, and you can think of the same thing for a basic solution. How do you make a solution basic? Well, you dissolve a basic substance into it. You put some soap into it. So that's one answer to the question, how do you make a substance acidic, how do you make a solution acidic or basic? You add a basic substance or an acidic substance to it. But there is a default way by which a substance that water can have hydronium ion or hydroxide ion. And this is a very fun thing called autoprotalysis. So bad name, autoprotalysis. It sounds like a German count. Introducing autoprotalysis. Okay, maybe it doesn't. What is it? Well, it's this very simple notion that here's a water molecule, and I'm going to call it water molecule 1 by putting a 1 there. Okay? And what is it doing in solution?
Random walk.
It's doing the random walk. Thank you. You see? The answer, all you got to say is random walk from us, any question. And then here comes, it's going this way, randomly walking, and it slams into this poor, unsuspecting water molecule 2. There it is. So water molecule 2 is minding its own business over here, and along comes randomly walking water molecule 1, and they slam into each other. Bam! And every once in a while, that one of those can react with another one of those. So this is again the reaction being they slam into each other by the random walk, and this one loses a proton to that one, so that we end up with number 1 being something we can there's your H3O plus, and number 2 gets stripped of a proton, and it becomes OH minus. So again, 2 happily randomly walking water molecules. One I've labeled 1, the other I've labeled 2. They slam together by the random walk, and every once in a while, this one, number 2, loses a proton, giving us H3O plus OH minus. And that is called autoprotalysis. The auto means self or, self-protalysis, auto-self-protalysis. So protalysis means generation of a proton. All right, so now let's leave out the random walk and just write it as a chemical reaction. So let's leave off the random walk and just write it as a chemical reaction. One water molecule, happily randomly walking, slams into another molecule to give occasionally an H3O plus and an OH minus aqueous. And we'll call this liquid plus liquid. Or another way that we often see it written is 2H2O plus liquid goes to H3O plus aqueous plus OH minus aqueous. So we got lots of ways to depict this, but it's all meaning the same thing, that you end up with hydronium ion and hydroxide ion. Another equally equivalent way of writing this is to even get lazier and say so how we depict this is up to the individual taste. This for me is a very good way to depict it because it shows the two water molecules are going to slam together, yielding hydronium ion and hydroxide ion. This is sort of a lazier way to depict it. You're just showing two water molecules giving hydronium ion and hydroxide ion. This is an even lazier way to depict it. Just one water molecule falling apart to give a hydronium ion and a hydroxide ion. But all of these are equivalent ways of depicting the same thing. Now, so autoprotalysis is the bottom line mechanism to put hydronium ion and hydroxide ion into water. No basic substance, no acidic substance, purest water you can get your hands on, and it's going to have both hydronium ion and hydroxide ion in it. But we can learn something here, very important, and that is any way we depict it, by any one of these three depictions that I've given here, we always end up with one hydronium ion and one hydroxide ion. No matter how I depicted it here. One hydronium ion, one hydroxide ion. One hydronium ion, one hydroxide ion. Now that's important because that means that if only autoprotalysis is going on, you got ultra pure water, you got no acidic substances, you got no basic substances. So in ultra pure water, in pure water, we know because of autoprotalysis that those concentrations have to be the same. They have to be the same because for every one H plus, I get one OH minus. And so that conceptually is what we mean by a neutral solution. A neutral solution is a solution where the hydronium ion concentration is exactly equal to the hydroxide ion concentration. That is a neutral solution. So in an acidic solution, now we can go back now to Arrhenius's definition, and we can say that helps grunting. So now we can say an acidic solution has concentration of hydronium ion greater than hydroxide ion. A neutral solution, as we just defined it, has hydronium ion equal to hydroxide And a basic solution is the opposite case. So if we start with just pure water, we're right here. Like my drinking water, squeeze a little lemon juice in. Now you got H plus greater than OH minus, that's an acidic solution. Like, maybe my mom, was feeling sorry for me and she didn't wash my mouth out with soap. She put the soap in a glass of water and made me drink it. Well, I don't know which would be more cruel, right? Well, in that case, the water would have a higher hydroxide ion concentration than the hydronium ion concentration. It would be basic. So very simple ideas. Now, let's take it a step farther. Let's go back to that neutral solution resulting from autoprotalysis. Went to college with him. Let's go back to that autoprotalysis reaction. I just erased it, didn't I? And let's just do it this way. I like this depiction. Again, we've already noted that the definition of that neutral solution is as depicted there. Hydronium ion is exactly equal to hydroxide. But what is that concentration? Well, we can get that by measuring the equilibrium constant called Kw. This is the autoprotalysis TALY constant. So it's the equilibrium constant for that reaction that I've drawn here, right here. And we can write what we know that equilibrium constant has to look like. Again, we write that because we've got hydronium ion and hydroxide ion as products of the reaction. And pure liquid water is the reactant, therefore no concentration term for pure liquid water. And as it turns out, so 10 to the minus 14. Now, what do we learn? We learn that the autoprotalysis reaction is very much a reactant-favored reaction. Very, very much a reactant-favored reaction. Again, we think about randomly walking water molecules. The vast majority of time that randomly walking water molecules slam into each other, they simply bounce off unscathed. That equilibrium constant tells us that it's a very rare encounter indeed that results in the reaction occurring at room temperature. Now, we've already established that all equilibrium constants are temperature dependent. All equilibrium constants are temperature dependent. And what would you think about this constant? Goes up with temperature, goes down with temperature. Goes up with temperature. The equilibrium constant gets bigger because the energy of the random walk gets bigger. Raise the temperature, these things are slamming into each other harder. Molecules are like little hammers. They can pound other molecules into submission. So at room temperature, that Ka is 10 to the minus 14. It can be substantially higher at bigger temperatures. So, but we're going to worry about 10 to the minus 14 as our number here. Now, that number then allows us to quantify what these concentrations are. In pure water, we know that the hydroxide ion concentration has to equal to the hydronium ion concentration. Now we got the equilibrium constant, and we can quantify that. Now we have the equilibrium constant. We can say, all right, what do I know here? I know it's 1 to 1 in pure water. So I'm going to just write it this way, since H3O plus is equal to OH minus in pure water. Then we can take our Kw expression, which is the concentration of H3O plus times the concentration of OH minus is equal to 10 to the minus 14. And we can say, well, since they're same, I'm going to plug in H3O plus for OH minus. That means Kw is H3O plus squared, which is 10 to the minus 14. So now we can simply say, great. It's like a workout. I should put weights on this, and that way get more exercise. It's like bench pressing. Okay. Alrighty, now, so that allows us then to say that in pure water, H3O plus is equal to the square root of Kw, which is equal to the square root of 10 to the minus 14, which is equal to 10 to the minus 7 molar. So in pure water, at 25 degrees C, H3O plus is equal to OH minus equal 10 to the minus 7 molar. Yeah? So 10 to the minus 7 molar is our neutral solution. 10 to the minus 7 molar H plus, 10 to the minus 7 molar OH minus. And now we go back to our definitions that the Colonel gave you at the beginning of the semester, that our definition of a high concentration is the 0.6 molar sodium chloride in seawater. And then we went down all the way to a very low concentration. That was our roughly 50 nanomolar allowable lead in drinking water. So we got this huge range here from 0.6 molar high to 50 millimolar, 50 times 10 to the minus 9 molar, very low. And you can see that this is pushing that very low limit. So again, this is why I gave you these limits, so that you can now, in your own head, sort of get a feel for what kind of concentrations that we're talking about. These are low concentrations. And 10 to the minus 7 molar. Now, that then, as we said, leads naturally to the notion that there's an easier way to express all this, and that's by the pH scale, right? So P of anything is negative log of that thing. So let's hold on to that for a moment. Ow. So that then leads, so we are perfectly correct in saying that vinegar solution has a hydronium ion concentration of 10 to the minus 3 molar. Nothing wrong with that. I'd like the hydronium ion concentration in my pool to be 10 to the minus 7 molar. But that's cumbersome, and so that's why we developed the pH scale. pH is negative log of the concentration of the hydronium ion. So P with something else there means negative log of. So in mathematics you see P of a lot of things. P just simply means negative log of. So pH is negative log of the hydronium ion concentration. And that makes things so much easier because our neutral solution has So that means it has pH is negative log of the number 10 to minus 7. Well, log of 10 to minus 7 is minus 7, right? Log of the number 10 to minus 7 is minus 7. That's why this negative sign is here, because that makes everything positive. So now we can take all the things we just said about hydronium ion, hydroxide ion, and we can say that our acidic solution has pH less than 7.0, meaning a higher concentration of hydronium ion. We can say our neutral solution has pH equal to 7.0, and we can say our basic solution has pH greater than 7.0. So you know all of these things. And again, I make this point that it's so much easier to tell my pool guy I want the pH of my water 7 than to tell my pool guy I want the hydronium ion concentration in my water to be 10 to the minus 7 molar. There's nothing magical about pH. It's just a great contraction in the number of words you have to use. Now, here is, let's see what we got here. Yeah. All right. Okay, so good. So now, I want to return to these two forms of now the autoprotalysis constant. So we wrote Kw, which is H3O plus times OH minus, is equal to 10 to the minus 14. We can solve that equation for either H3O plus this, believe it or not, is a very powerful equation. And let me state to you clearly why it's powerful. This equation says if I know the concentration of hydroxide in a solution, I can calculate the concentration of hydronium ion. And this equation says if I know the concentration of hydronium ion in a solution, I can calculate the concentration of hydroxide. So, very, very important point to get into your head. For any aqueous solution, at 25 degrees C, this equation applies. So, the equation could be acidic, the solution could be acidic, the solution could be basic, the solution could be neutral. This equation always applies, always. For an acidic solution, this equation is true. For a basic solution, this equation is true. For a neutral solution, this equation is true. This is an important point. This equation applies to all aqueous solutions at 25 degrees C. Now, why is that important? It's important because if I know this, the hydroxide, I can calculate the hydronium ion. Or I can turn it around. I can solve it for hydroxide. I can solve it for hydroxide. I can take Kw, it's hydronium ion concentration, times hydroxide ion concentration, equal 10 to the minus 14. And I can do the opposite. I can solve it for hydroxide. So it's very powerful because if I know one, I can calculate the other for any solution, whether it's acidic, basic, neutral, doesn't matter. If I know the hydronium ion, I can calculate the hydroxide ion. If I know the hydroxide ion, I can calculate the hydronium ion. And we can state this in the P format. Unfortunate choice of words, I guess. Uh-oh. We can put this in the P format, pH and POH. We can say we can define this thing called POH so we got pH, the negative log of hydronium ion concentration. We got a corresponding parameter, POH, negative log of hydroxide ion concentration. And we can take our handy-dandy equation that we know always to be true. And we can take the P function of both sides. And if you do that, you find out that pH plus POH has to equal to 14. pH plus POH of a solution has to equal to 14. So again, it tells you the same thing that I told you previously. So this is just another, you might call this the logarithmic form of that equation. So this right here, pH plus POH is 14, is the logarithmic form of this equation obtained by simply taking the negative log of both sides of the equation. So I'll start you off. The negative log of 10 to the minus 14 is 14. That was easy, huh? Negative log of 10 to the minus 14 is 14. Take the negative log of this side and you get pH plus POH. So again, why is that important? Same thing I said here. For any aqueous solution at 25 degrees C, this equation applies. And likewise, this equation applies. So these are equivalent forms of the same equation, just logarithmic versus non-logarithmic form of the equation. Now, so again, what that means, taking specifically this equation, so again, what this means, so again, for any aqueous solution at 25 degrees C, this equation applies. That equation applies. So again, what that means is you can solve it if you know the POH of the solution. If this is known, then you can calculate the pH. Likewise, solve it for POH. So in this case, if you know the pH of the solution, you can calculate the POH. So you've seen all of these kind of things before, I'm pretty sure, starting back in elementary school. Oops, what is that? I'm not picking that up. So I'm just quickly reviewing them here, but this is an important part of it, the notion that if you know pH, you can calculate POH. If you know hydronium ion, you can calculate hydroxide ion. And you'll see this on exam 1 for sure. There will be problems that say, the pH of a solution is 6.2. What's POH? Or POH of a solution is 12.5. What's pH? Or the hydroxide ion concentration of a solution is 6.2 times 10 to the minus 3 molar. What's the pH of the solution? Lots and lots of different simple problems that you could encounter on exam 1, basically asking you to manipulate this single equation. And I'm sure you'll encounter such problems on your on exam 1 next week. Couldn't be next week already, could it? But it is, unfortunately. All right, now, how do we measure pH? There are two common ways to measure pH. One is with a pH indicator paper. So litmus paper, everybody's heard of litmus paper, right? Litmus paper is a strip of paper that has a dye on it. And the dye changes colors depending on the pH of the solution. I do this with my pool water. I take this little strip of paper and I dip it down into my swimming pool, and then I hold it up against a color standard. And if that thing is bright pink, then the pH is too high. If the thing is sort of an orange color, the pH is too low. So litmus paper and things like it have been used for over 100 years to determine roughly the pH of a solution. Now, the more modern way is to use a device called a pH meter. Use a device called a pH electronic device. Called a pH meter. And the heart of the device is a thing called a pH electrode. And that pH electrode produces a voltage proportional to the hydronium ion concentration. So, who's used a pH meter? Look at this. This is the most common piece of analytical instrumentation in the world. Every laboratory, whether it's a microbiology lab or a chemical engineering lab or my labs up there where we're doing all sorts of weird stuff, we're messing with life. Life, I say. Tell you about that later. But you'll find a pH meter in any laboratory. And that is an electronic device, the heart of which is the pH electrode, and it's magic. You stick the pH electrode into the solution, and it reads out the pH on a dial or a display in front of you. So that was an amazing device. It was discovered in the late 19th century, at least the parts of it. It got commercialized by a guy named Arnold Beckman, who was a chemistry professor at Caltech in the 1920s. Arnold Beckman was an electronics whiz, and he made this first device, electronic box that'll measure pH. And so he starts publishing papers with his new box that he made that measures pH electronically. And people from all over the world start saying, hey, can you make me one of those boxes? So he started a company in his garage to make these boxes. And that became Beckman Industries, which still exists, which worldwide does hundreds of billions of dollars worth of business each year. So Arnold Beckman, who is no longer with us, made a fortune in science by inventing the device that you use to measure pH. All right, we'll stop there.